the world as we know it is built on quantum mechanics, quantum interactions. The natural world, the table, the microphone, we have this podcast, the silicon chips that power the computers, molecules, drugs. At the fundamental level, all of that is all quantum. And the beautiful thing is with a quantum computer, we'll actually be able to understand what's going on at that fundamental level for the first time ever. At the moment, we're just kind of making approximations and being clever, but it's, okay, how can we know if this drug will work in clinical trials before it gets there? How can we make better fertilizers so we can feed the world? That's just all down to understanding nature at the end of the day.
Disruptors and curious minds, welcome to another episode of Thinking on Paper. My name's Jeremy. This is Mark. We unpack the future with the people building it today.
Our guest is Brandon Severin. He's the founder of Conductor Quantum. Welcome to the show, Brandon. Thank you for thinking on paper with us.
Amazing. Thanks for having me on, guys. Pleasure to be on here.
Tell us about this Google announcement that just came out, why it's important, and why it has this interesting tie to the nature piece that we're talking about.
Yeah, the Google announcement was very timely. It's important because, one, look, the Google quantum team's great, and they've basically been able to show that they have a chip with over 100, quantum bits, qubits, which they're able to control them, operate them, but most importantly, they've developed a new algorithm that allows them to start looking at how atomic nuclei interact with each other. How we do this normally is using NMR, so nuclear magnetic resonance, and it's how you figure out the structure of molecules. And we've been doing this for, decades now, and Google's basically figured out a way to enhance NMR analysis on a quantum computer. So it's that direct correlation of, okay, I have this atom here and it's, let's say, an oxygen and it's bonded to other hydrogens. And next to it, I have a carbon. What is the structure of that interaction? Like, what does that shape of that molecule look like? And we've basically been doing that classically using NMR, but with now this latest algorithm from Google, we can get more of an idea of that atomic structure at longer ranges. And the way they've done it is actually quite clever, to be honest with
you. How have they done
it? Yeah, so it's this, the problem with NMR spectroscopy is that it's very short range. i.e., if I have, let's say, an atom here and an atom here, I can sort of figure out their interactions. But if I go further along the molecule and I have an atom over here, I don't really know how this atom all the way over here interacts with this first one. And what Google have done is basically put together an algorithm. They can actually figure out those longer range correlations to this nearby atom. And that allows you to basically have more of an idea of what the structure is. You don't need to kind of second guess what's going on. Now, they've done it on relatively small molecules, like 18 atoms, 28 atoms or so. But it's very promising. And the algorithm itself, how have they done it, is basically simulating, the nucleus of this atom as an individual qubit on their chip. And they basically run a plethora of operations to get the chip into a certain state. Then they basically give one of those qubits a little kick, and then run that first set of operations in reverse across the rest of the chip and see how what they get back, is how it's different to what they sent, basically. And that gives you an idea of how that first qubit is coupled to all the other qubits. And that you can sort of think about that then as the nuclei. So the nucleus, how that nucleus of your physical atom is coupled to all the rest of the atoms in your molecule. That's effectively what they've done. And look, it's a first. They argue that no classical computer can do what they've done as fast as they've done. And I think, first glance at the paper and what I can tell so far, I think it's actually a reasonable claim. Of course, I think someone will probably be able to work really hard and come up with an algorithm that can run on a classical computer. But for now, I mean, Google has a great result, right? Like it
Can you give us
works.
like a real life example of what that algorithm or what future iterations of that algorithm could be used for
Yeah.
in a useful way?
Any molecule where you want to know, you synthesize the molecule in a lab, having an idea of what that molecule looks like, its structure is very important as to how effective that protein, that drug will be. At the moment, this was kind of the big idea with AlphaFold and kind of predicting protein structures from Google DeepMind. But bear in mind, that's predicting protein structures, not actually calculating them physically with hard evidence. And that's what this NMR spectroscopy brings insight to is, okay, what is the shape of this organic molecule? And therefore, what's the structure? How well will it bind to, a harmful disease, your cells, a viral cell, for example? That's where this goes further down the road. And of course, it's small molecules now, but it's the fact that they've been able to do this is, I think, really, really impressive. The bearish case for quantum, to be honest, is actually the lack of algorithms. It's okay, I give you 1 million qubits today. How will you use them? Like no one really knows. But we're already seeing that, okay, as we get more qubits, we can develop better algorithms and test them and see how they work.
What's the bottleneck in creating algorithms, quantum algorithms?
Nature. Maybe you don't create an algorithm, you simply find, you discover that where it exists in nature.
Yeah, pretty much.
Is that a stupid comment?
No, not really, because you're effectively trying. It's this kind of going back to the intro to the podcast, which is like you have this weird limitation of you want to simulate nature, but you also only have so many qubits. So then you kind of want to develop your algorithm for the computer you have access to, because then you can also verify that it works. Like the Google team put out this whole thing about like this is the first quantum verifiable algorithm. It's kind of true. Like they just get a number back, which means that if you had a quantum computer, you could run their algorithm, check the Google result, and actually, if nature itself could run the Google quantum algorithm and check the result. That's the beautiful thing about it. When you think about it, that's the level we're playing at with quantum computing.
The first thing we talked about, more qubits, or in the intro, I talked about the more qubit camp versus the better qubit camp. And then there's also the next piece of the puzzle is, okay, which type of quantum, which type of qubit is the best and which one you're using. So let's pick a couple. One, we're going to stay with spin because that's what you're involved with. Let's talk about spin and let's pick like trapped ion. So let's look at spin and trapped ion. Can you break down both of those two and tell me about the difference between one and the other?
Everybody will say their qubit is better than the other person.
Absolutely, but Ford's better than Chevy, Toyota's better than, yeah,
So
right.
they've all been on the podcast and they've all said that their qubit is the best. We've had
Literally.
Q1, we've had IBM.
Yeah,
They've all said
literally.
the same. Yeah.
So let's start with trapped ions. They're probably one of the few qubits that actually when you hear them, they describe what they actually are, where you have literal ions, so calcium ions, cesium ions, whatever. Well, actually, that's more the neutral atom, but calcium ions. And you trap them in space. You have a column of ions trapped. How do you do that? Physical lasers. You literally, use this laser cooling effect where you have ions floating and you shine a very well focused laser on them and you trap them within that laser beam. Kind of like something out of Star Wars, like, the Force. And you effectively start to build, I kind of describe it as like a Newton's cradle, but with physical ions. And the beautiful thing about ions is they are ions. Once you've trapped them, they have their kind of this well that they sit in and you can operate on them. And the beautiful thing there is well controlled, great environment, what's known as the key metric in terms of better qubits is very high fidelities, meaning that when you tell your qubit or your ion to be in state 1, it is in state 1, 99,000 times out of 100,000. Whereas other qubits don't necessarily have such high fidelities, but they'll have maybe other benefits like long coherence times, meaning your qubit stays in this quantum state for a very long time.
If I could just unpack fidelity a little bit, is that kind of a ratio or the combination of gate speed and coherence time together, or no?
It's its own thing.
Okay.
It's almost, you're literally measuring the reliability of your qubit.
Of it being in this state or this state.
Precisely. Or
Got
when
it.
you do and then that there's almost like more layers of fidelity. So I perform an operation on my qubit and I expect this answer. Is it correct? How many times, out of 100 is it correct? Basically. And that could be, let's say, your single qubit gate fidelity. And then you pair 2 qubits and you do a 2 qubit gate and you get a 2 qubit gate fidelity. Getting down the rabbit hole here, but
does the fidelity decrease as the more qubits you have?
Good question. From what we're seeing, yeah. So single qubit gate fidelities are typically always higher than 2 qubit gate fidelities. I think it's just by nature of the system, right? Probabilistically, it's harder to do a 2 qubit gate more reliably than a single qubit gate. And by that, we mean like you're pulsing on 1 qubit, you're, let's say, rotating it from 0 to 1, and then you're doing the same thing on the other qubit and you're measuring out the combined state of those two. And there's just more things that can go wrong, right? As you add on that extra qubit. But, with good quality single and 2 qubit gates, you can build a quantum computer. So once you've met a good threshold, then you can argue, okay, with X number of qubits and this level of fidelity, I'm good to go. We've ticked the boxes. But the more qubits you have, it gets difficult to manage. So then you need extra qubits to correct for these errors, basically, of your qubit that you want to use for logical operations.
That's the more qubit versus better qubit.
Exactly.
Having one to back up the one that doesn't behave properly, right?
Exactly. And it's not just one you need to back up. It's like hundreds, if not thousands of qubits, that you need for one logical qubit. You need like 1,000 error correcting qubits.
Thanks for diving into that stuff with us. Back to the trapped ions. You've got this thing suspended in a vacuum. It's kind of
it's literally a vacuum trap.
This little vacuum trap. It's kind of like Ghostbusters when they suck in the ghost. It's an ion trap. It's probably similar to that tech, right? Ghostbusters were quantum.
Look, if that works, 100%. And yeah, you have it in this trap like a Newton's cradle. Then you fire different electromagnetic waves at it. So whether it's laser light or whatever your ion of your choosing, depends on basically the frequency or wavelength of light you shine on. So red, blue, green, whatever. And that excites your ion. That excites basically the electrons in that ion to different levels. Einstein, going, back to the OG of quantum mechanics again, when that ion loses its energy, it emits light. And then you can measure that light. The hard part is measuring the light, because that light's going to come out as a individual frequency. It could get absorbed by anything in your huge vacuum. You need to collect it. You have all these different efficiencies of detection. You need to collect the light. It needs to transmit down a fiber, and then you need to be able to actually detect it with a photodetector. That being said, the ion trap teams that are working on this, Oxford Ionics, now acquired by IonQ, Quantinuum, they're great at doing this stuff. Really, really good. They have some of the highest qubit fidelities in the world.
Let's start talking about spins. There's like a silicon layer, and we're literally poking holes in the silicon layer and trying to convince electrons to jump in those holes and stay there. Let's talk me through that, man.
Yeah, what is a spin qubit, I think is the question.
There's 2 ways to approach this. There's the very bottom up way, where you start with the physical spin qubit, or there's a top down way, which is you start with a silicon chip. Let's start with the bottom up way, because that's the fundamental question. What is a spin qubit? So a spin qubit is an electron orientated in a magnetic field, and you can view that electron similar to this NMR, nuclear magnetic resonance. That electron behaves as like a tiny bar magnet. Similar to the magnets or a compass needle, on planet Earth, it wants to align with the magnetic field, right? Your compass needle wants to point north. Kind of similar feel with your electron. It either wants to be spin pointing up or spin pointing down. And up, let's say, aligned with the magnetic field, or down against it. And those are your two quantum states. Those are your two bits, spin up, spin down, 0, 1. Now, the hard part is, well, okay, great. And I think, like, arguably, you could say this is probably like one of nature's most fundamental qubit. You can't get smaller than an electron spin qubit. Then the hard part is, okay, how do I isolate an individual electron? Like, good luck. And that's where the silicon comes in. That's where we come in as a company, which is you look at the transistors on your desk, the transistors in your phone. Those are basically tiny, tiny switches. You've got like 50 billion transistors in your pocket right now that allow you to control billions of electrons flowing across them per second. And that's on or off. The current's flowing, the electrons are flowing, transistor's on, current's not flowing, electrons stop flowing, off. And it's like, okay, can I turn that into a quantum bit? I got billions of electrons flowing, but I only need one electron. And the genius part of spin qubits is if I just slightly modify my transistor to give me a bit more control over the flow of electrons and still keep the same semiconductor process that prints trillions of these transistors every day, but just say, look, let's just kind of tune this transistor, kind of like Fast and Furious. You tune up a car, add a bit of NOS or whatever. Yeah, but very small, very small. Can I start isolating individual electrons? The answer is literally, yeah, you can. And the trick is basically a transistor works on having what's known as a gate electrode. It gates the flows of gates the flow of electrons going from one side of the transistor to the other. If you add a few more gates, you can basically start to isolate electrons between these gates. Well, it's not between, they're physically underneath these gates. All of these gates is all controlled by standard voltages, classical electronics. So no lasers, no vacuum, same way your electronics work now. And if you finely tune the voltages you apply to those gates, you can isolate an electron. You can make it jump to the left, jump to the right. You can have it sit there for, what seems like an eternity in the quantum world. In reality, it's not that long. I mean, we're talking like milliseconds. But because going back to, your point on operation speed, you can get that electron to flip between state 0 and 1 on the order of nanoseconds. Your gate speed is on the order of nanoseconds. So if you have milliseconds of your electron living in this quantum world that you've built for it, you can do thousands and thousands of operations within that time. And
so
that's
you're
just
taking an existing chip and using what's happening on the transistors and going down to the quantum level and controlling the electrons which are already passing in their billions through these gates.
Exactly that. So it was like, I think the late 2000s, it's like, oh, we've reached peak semiconductor, the node size can't get any smaller. The transistors are so small. You used to say like electrons could tunnel from one side to the other. We're like, that's not a bug. That's a feature. Great.
Well, that's the next step of evolution, technological evolution. Yeah, it's incredible. So the Google algorithm, you said and nature could run that algorithm, any quantum computer can run that algorithm. So if you have a trapped ion quantum computer is superconducting or one of your spin qubits, it can run that algorithm. So there's no, algorithms are qubit agnostic. They can run on any system.
Ideally, yes. I mean, there are certain algorithms that will pertain themselves better to certain systems. Like it's just more easy to visualize and physically understand how that interacts with the underlying hardware. But that's the whole point of these algorithms, is that, regardless of your quantum sort of basis set or modality, they work because algorithms are effectively gates, the same way that the algorithm, let's say we run on a laptop, should also work on a classical computer made out of whole punch cards or buckets of water. It's just operations on zeros and ones, effectively.
Whenever we talk to a quantum guest, I always have this have this picture in my mind of like a ringleader taming a lion under the big top. The lion's the qubit, and we're trying to like tame the lion in the corner. And then like the split second the lion's tamed, Mark's got to come over and whisper a calculation in its head or a data set for it to rip on. Like,
Yeah.
It's like a quantum circus, Jeremy.
There it is.
A quantum circus.
Trademark, you heard it first on Thinking on Paper, the quantum circus.
In the quantum circus, where you have all of the different systems entertaining the crowd, what can you do with a spin qubit that you can't do with other qubits?
Ooh. The big thing for spin qubits is that the manufacturing chains are already in place. And it's not necessarily what we can do with them, right? That's not answering the question, but it gives you an idea of the sense of scale that spin qubits can approach without having to like kind of reinvent, a whole new manufacturing paradigm. Because we are really trying to like leverage a $1 trillion industry, a multi-trillion dollar industry that's been like perfected by humankind for the past 50 years. When you think about, when I think about like the most impressive technology ever, it's definitely just what we can do with, an EUV machine, or whatever you use basically, but to pattern these silicon wafers into transistors and, push humanity forward in ways we haven't seen before. Spin qubits are unique in that. Photonics come close, and that, you can also make those in industrial fab, but you kind of need to really change the recipe. Physically, what makes a spin qubit unique is you can move them. There's a lot of work in the spin qubit community now where people are literally figuring out how to, what's known as shuttle, move these qubits across. So we talked about isolating an electron in your transistor, but let's say you want a qubit here to talk to qubit here on the other side of the chip. How do you do that? Do you use some quantum entanglement at a distance sort of effect? It's too far for that to happen. You actually can shuttle these qubits across the chip, get them to chat, move them back.
Get them to chat. So the lion tamer thing is real.
The lion tamer thing is real. And the amazing thing is, you've picked the perfect animal, which is it's basically part of the cat family. And you can go all the way back to Schrodinger's cat, right? Like, you're born natural. And that's effectively what a quantum computer is you've got Schrodinger's cat, which is this, old thought experiment of what a qubit is and measurement and collapse and whatever. But you've got a cat in a box. Is it alive or dead? Well, quantum mechanics basically says that once you open the box, the cat used to be in superposition, i.e. being both alive and dead or neither nor at the same time. But once you open the box, you measure it and it collapses into one of those states in being either alive or dead. With a quantum computer, you're basically trying to keep the box closed while you manipulate the cat into the likelihood of being alive or dead when you open it without killing the cat or keeping it alive. So literally exactly your lion tamer circus is
very interesting. So how do you, the biggest hurdle for me to overcome in understanding all of this when I first got into it was how literal I took the observation. You picture someone standing there in a lab coat with a clipboard observing, and nothing quantum can happen until this observation takes place. And then who's observing the observer, observing the observer? Like, how do you talk someone out of that theoretical place into let's land the plane and get tangible with it?
Oh, it's tough. I mean, because
it's hard, right? Yeah.
Yeah, because the deeper you think about it, it's very philosophical. And I mean, there's still two camps of interpretation of this, right? There's known as what's the many worlds theory, and there's the Copenhagen interpretation, and even that's not necessarily just the idea of the observer, but it's related. And, there's this joke, a great way of understanding the difference between the two is this joke is just like, if I'm in Copenhagen and you see me there, that means I'm there, right? Whereas the many worlds theory says, well, I could be in Copenhagen. I could be somewhere else in a different universe. You're just not part of that universe. What you believe is up to you. I prefer the many worlds. I think it's a lot more a much more interesting way to live your life, knowing that in some other universe, your lion could be still alive or dead, depending on what world you want to live in. Look, the thought experiments go on and on and on, and some have actually never been solved. Is it, Wigner's friend and something like that.
Actors or observers, acting, observing. Yeah. If we're going to continue the quantum circus analogy and wrangling these cats, how are you wrangling the cats? So you're doing something different, aren't you? Because you're using artificial intelligence to wrangle the cats, to wrangle the qubits, to control the qubits. Is that correct? Can you bring artificial intelligence into this conversation and how you're using it?
We're just trying to get the cat into the cage to start with. When we think about our billions of electrons, it's like, okay, well, I need to isolate one. So basically I need to kind of form my qubit. I need to get my cat into the circus. And that's where we come in right from the beginning. And so the AI comes in where it's, okay, I'm applying these voltages to isolate my electron or puddles of electrons, let's say 10 or so, and then I can slowly deplete that puddle so one's left. And that's a really hard thing to do. But the joke is what you wouldn't believe is you learn how to do this as part of your PhD if you work in spin qubits. You learn how to manipulate those voltages, let's say 5, 10 different voltages or so, by hand, so you can isolate 1 or 2 electrons next to each other. I did it myself at Oxford in the first 2 weeks. My PhD, it took me weeks. I didn't even get close. I got to maybe 50, 100 electrons or so. I said, like, no way. If we want 1 billion qubits, how's this going? You can't have 1 billion Brandons, right? And that's where automation AI comes in.
That's a different thought experiment.
Well, one in each of the worlds, right?
Literally, yeah. One in each of the worlds, you're fine. And that's where the AI comes in, which is basically, this is like loading the cat into the circus. You can think about it as like the bootloader for your operating system on a classical instrument. You press that power button, it fires off a whole sequence of instructions as to what voltages to set each transistor and to load what software from where. That's what we're building from the ground up. So it's controlling those voltages such that we can first form that qubit. And once we've got it, it's okay, great. Let's do operations on that qubit. The qubit's gone out of whack. The electrons disappeared. Let's get it back. Let's recalibrate it, things like that. And to go all the way back to the Google result, I think that's why it's so hard. These qubits don't come for granted. Even when you have them printed on a chip, you really need to calibrate them and fine tune them to start doing interesting things with them.
Who's this for? Who should be listening to this going, okay, I want to learn about these different AI models that you have?
First of all, it's for ourselves. We are our own users, as well as other people in the spin qubit and quantum community. The models are effectively analyzing the signals you get from current flowing through that transistor, saying, okay, based on, let's say, these certain changes in current, what's the next best voltage I should apply to get me closer to getting a good performing qubit?
Ooh, just like the word predictor root of what LLMs are doing anyway, right?
Yeah, exactly.
We're just voltage predicting.
Yeah.
If Mark is making spin qubits and wants to make more of them, he could probably come to you and say, help me automate this process. I want to make more spin qubits. Yeah. But say I've got a pile of wrangled cats back there. I've got a lot of spin qubits, but they aren't behaving properly. Can you help me understand how to make those work better together? Is there an efficiency angle to what you're doing as well? Optimization?
100%. Software can work at night. It can work at all times of the day. PhD students and researchers get tired. And I think the important thing to understand is this is basically the precursor of an operating system. And I think that's where Mark one day will interact with this software without even realizing it. It's okay, I want to run my quantum algorithm. I want to design a new drug. You're doing that through Conductor, Conductor OS or whatever it's called at that point in time. And that goes and compiles all the way down to basically these voltages pulsing on individual qubits, individual electrons.
We have a book club and we just finished The Empire of AI. Karen Howe's look at the start of OpenAI and a lot of the behind the scenes things that a lot of people... Really fascinating read, but we break it down chapter by chapter. But the reason why I bring that up is the way kind of the rules of the road, as we called it in book club for AI, was like, hey, we just got to get more GPUs and we just got to scale. And then we'll figure out all the shit when it comes down and, you know, what to do with that and how to manage it. Are we doing it the right way for the right reasons? Talk to me about what the quantum industry is doing, right? Is there a big push to drive and scale qubits like there is GPUs? Is there any correlation there? Are you seeing a different approach, a better approach, a worse approach?
The industry basically splits up into two camps, which is I can build my quantum computer one qubit at a time, or I can think about, okay, we're going to need at least 1,000,000 qubits to do anything useful. And by qubits, I mean physical qubits due to this error correcting problem we have. So how am I going to build the foundations in a way such that I can build for 1,000,000 qubits? It's in a way, it's like, I want to get to the moon. Do I try and build a rocket ship, or am I there, assembling ladders in a sense? What camp you sit in, I think heavily depends on who you are actually as a person, in my opinion, and your thoughts of what's possible in terms of scale. There's a typical sort of thing where like often the people in the first camp of one qubit at a time is often very much like a university spin out sort of mindset where, and this is really how quantum started, it's like, well, at least physical quantum computing, which is I'm doing an experiment in my lab. Oh, it just so happens you can actually build a quantum or a qubit out of this. Maybe we could turn this into a quantum computer. And that's really how a lot of the early quantum computing startup came to fruition. And I was like, okay, but hold on, we need millions of these qubits. Just how do we get there? What platform will actually get us to millions and millions of qubits? How will we make them? How will we have the power to cool those chips down? Where will that power come from? Where will we have enough water to keep these chill, basically these cryomech pumps to keep your pulse tubes cold? All these things you need to think about when you're thinking about like million qubit sort of scale is very different to, I just want to get 3 qubits next year, then 4, then 5, and so on. And I think that's really what makes spin qubits very unique. Is manufacturing wise, we know we can make chips with the potential to house millions of qubits. But then at the initial Lego block stage of, well, okay, but how can we get our 1, 2 qubit gates fantastic? How can we deal with this control and calibration problem that we're solving, which is just a huge bottleneck to scaling? Because we know we can make excellent 1, 2 qubit gates in silicon. We've broken, the required thresholds and records for that. The problem is, well, okay, if I give someone a 4 qubit system, which is a spin qubit, that's like, 20 individual parameters they need to optimize to just get the thing working and on. And it's like, how does that scale to millions of qubits? So we're very much in that million qubit thought process of that's where you want to go. Let's build for that. When you see the pictures of the beautiful Google Willow chip and they hold it in their palm, right? And it's like, this is the Google Willow chip. It has 105 qubits, or 103 qubits. It's like such a feat of engineering, for them to be able to do that. But like in a chip that size, for spin qubit, you can have like billions. They're just a million times smaller. But that's also the hard part, is they're so small, they're hard to control and so on and so forth.
Referring back to what Jeremy mentioned about the empire of AI, you went to Y Combinator, you work in Silicon Valley in a startup, you are living in this world. Is it a different kind of person who works in quantum that works in AI, but now you're bridging those two worlds? Do the two groups of people come together? What's the vibe? What's the culture of quantum?
What's the vibe? I think, honestly, the vibe is very... I'd love to know what the vibe of AI was like, let's say 10 years ago, because it feels like quantum's kind of like at that stage where we have like these amazing demonstrations and we can kind of sort of see this pathway to, oh my gosh, this is going to change everybody's lives, but we're not there yet, because AI in 2013, 2012, and cats and dogs and captioning images and things like that. Obviously, there are always going to be personalities, but the culture is very, very collaborative and supportive. And, to give you an example, during my undergrad, I mean, I did it at Oxford. And so like just across the street from my building, which was in materials science, there was a physics department. And in the basement, somewhere in that building was Chris Ballance, who then went on to found Oxford Ionics 2 years later, that recently got acquired by IonQ for like, I don't know, 1 billion or something like that. I met Chris Ballance because I was working on a quantum project for like a few weeks, which was, what would a quantum computer server farm look like? Who was the best person to talk to? Chris Ballance came across the road. Hey, Chris, what do you think this will look like? He goes, well, like it's going to be tricky. We have all these problems. We started chatting, and me and another group of students. So just to give you an idea, like, and I think we're kind of entering this new wave where before it was very much like professor of X group founded quantum company, and academia, there's always going to be rivalries, right? Because of effectively, what defines you as an academic is you being first to do something, your publication record, and so on and so forth. But I think now, the students of those professors and the students of those students are now forming quantum companies. And we're seeing like this huge community sort of grow, and everybody support each other in different ways. There's many quantum founders I'm in regular touch with, and I'm like, you're just seeing like the age drop and the community build at the same time as well. It's very small. I'm always surprised at how small it is, but because of that, it's very beneficial and very supportive. But, everybody kind of knows, right? Like, is ion traps going to win, or superconducting qubits going to win, or spin qubits going to win? I think though the smart ones among us also know, like, look, there's probably not going to just be one modality. And we're already seeing that. Google Quantum, for example, are doing great stuff with superconducting qubits, but so's atom computing and Quera with neutral atoms. And you can use their computer on Amazon AWS. Literally, you can log on and start running quantum algorithms. And arguably, they have more qubits. So we're already kind of seeing that, okay, it's not really winner takes all. And I think because of that, the community is still very supportive.
So our last question, which asks all our guests, from Kevin Kelly: what should humans be, and how does technology help us get there?
Humans should just be like, obey the golden rule. Treat others as you want to be treated. I think that having that rule is very human in itself, because it gives an idea of long-term thinking. It definitely leads to it. How do we get there? I think technology helps us get there by providing insights to other people's experiences. So whether that's through literally like media, discussions, podcasts like this, or understanding of suffering and how to cure that suffering, quantum computers, classical, whatever, solving technological challenges. Honestly, I really see it as technology is kind of like this eye opener for humankind. Because you kind of see already, right? Like you can know what's going on the other side of the world where you weren't able to do that, where you're just, like hunter-gatherer tribe in South American jungle. But then it's like, okay, what do you do about that? Does it affect you? Do you care? And I think, yeah, as technology progresses, you're actually able to impact other people in ways that you just weren't able to before, by flicking switches and playing with transistors and whatever. That'd be ideal. Literally, like, treat others as you want to be treated and leverage technology to do that, whether it's through spreading well, education, whatever.
The next best startup that will help that is a empathy activator.
I doubt it. I think
quantum powered.
Yeah, quantum powered empathy activator presented by your friends at Thinking on Paper. No, that's great. That's great. Well, what about a carryover question for the next guest? Can be about anything.
Kind of related to the first question, which is like, do you really care about what you're doing? Particularly like other technologists and founders. And also related to the previous discussion of like, the community of scientists building this technology is like, why are you doing what you're doing, and do you actually care? I mean, I know for us at Conductor, it's like, I couldn't think of doing anything else with my life. I really see a way that this is just how we have such a huge impact on the world. But I've also worked on projects where I'm just like, geez, man, like, can this be over already? Like, why?
Unfortunately, though, Brandon, this is thinking on paper, and all our guests care.
Good. Wonderful. Honestly, wonderful.
Man, what a conversation. Brandon, thank you so much for
thank you
for chatting with us. Anything you wanted us to ask that we didn't?
Why is it taking so long? Actually, I think is a good question.
Why is it taking so long, Brandon?
Honestly, I think it's concentration of human beings and resources. I think it's this approach where either you want to build a rocket ship or you want to build ladders. And we don't have enough people building rocket ships, in my opinion.
There's a finite supply of smart people. It was quite funny. Earlier you said the smart ones among us. And I was thinking, hold on, like, aren't you all incredibly smart?
You can only know so much about like your particular, like I know spin qubits. But it's like, can I design a quantum algorithm from scratch right now? Probably not. You know, the layers of the stack goes on and on. You know, could I run
You said probably not. We would say definitely not on our.
Well, I know it's possible, you know, because I've seen other people do it, you know, with a few years of hard study, right? But that's the thing, it's a few years of, you know, like building the tool set and exercising that part of the brain. I don't know. Look, it's different strokes for different folks. I do think like the progress we've made as a community is like just comical in terms of how good it's been. Like, you know, 20 years ago, people just didn't think it was possible to have a qubit. You know, and they also didn't believe you could rotate the spin of an individual electron. You know, during my PhD, I saw like teenagers do it in their lunch break as part of their labs. Right?
Okay, so on that, what do people think's impossible now that might in 20 years you'll look back and go, well, they're doing it now on their lunch break?
Yeah, the scaling argument of getting to millions of qubits. I think every quantum modality kind of has that, like, you know, we can make one, we can make two, maybe we can make 100, but how do we really get to 1 million qubits? What does that actually look like? Everybody's like, and some people genuinely believe it's just impossible in certain modalities because they're like, oh, the cooling requirements, the power. But I do think within 20 years, you will have millions of qubits and it'll seem like, okay, cool. When billions of qubits?
what's the okay? All right. What's the likelihood? I don't know. 7 years from now, someone figures out how to make one qubit so freaking magical and so useful that they debunk this whole scale theory. No, not at all.
No way. And the reason being is the numbers required are so ridiculous. You know, there's a great graph and study done literally by like DARPA, the US Quantum Benchmarking Initiative, where they basically say like, okay, if you get the qubit fidelity to like, you know, like 10 nines of fidelity or whatever it is, you will still need like 1 million qubits to run RSA or whatever, you know, to correct for those errors.
Okay.
Yeah, like, because to really give you an idea, right? Like, in terms of fidelity, the bits in your computer, they might, you know, make a mistake like 1 in like 10 to like the 23 times. You know, like it just never happens. Whereas the threshold for quantum computers is 1 mistake in 1,000, you know, like 99.9% fidelity. Big difference. And so you really have to be able to take out more errors than you are putting into the system. What could change is someone comes up with an algorithm that can take advantage of, let's say, lower fidelity qubits. And, you know, Google's done work saying, okay, well, in theory, you could run RSA if you have like this fidelity qubits and with 1,000 and whatever. But implementing that physically and experimentally, good luck. You know, IBM have the Tor codes. It's once again, it's that rocket ship. It's like, if you can make many qubits, you don't need to worry about that problem anymore. And you're going to need that number of qubits to do error correction in the first place. And that's why, yeah, we're like very, very focused on leveraging silicon technology, because we just know you can print these things in the masses.
There you have it.
Awesome answer. Thank you. A lot to think on. Thank you, Brandon. It's been an incredible conversation. More layers of quantum for us to unpack at a later date.
Anytime. I love talking about quantum. I mean, we went down the rabbit hole, guys, like thinking on paper.
We speak about a lot of technologies, but it just seems there's something about quantum that is different to the other technologies we speak about. And when we have quantum, maybe it's just because we know so little, and it's just so, nothing spikes our curiosity like this. And because it's so foreign, really, to us. But at the same time, it is us.
I think this is one thing I want to do as a company, is really like demystify this foreignness. Because, you know, there are certain ways of thinking about the quantum world that actually do make sense. You know, it's like, you know, you have a kid and you offer it 2 Mars bars, right? One in the left hand, one in the right hand. And it's like, okay, which Mars bar does the kid choose? Kid wants both of them, right? That's effectively your electron in superposition. It wants to be around this positive hydrogen atom as well as the other one, right? It wants to be in 2 places at once. And it sounds ridiculous, but hey, this is normal.
I love that. Kids are just, every time you speak to a kid, they're literally running through Schrodinger's cat experiments in their head, because they want it all.
100%.
Thank you. If you got here, you're a real, true, and I mean it this time more than ever, a curious mind, because some of that was deep, some of it was complicated, but all worthwhile. So thank you for staying with us to the end. If you have any questions on that episode, you want to follow it up, email us at hello@thinkingonpaper.xyz. Otherwise, comment, subscribe where you're listening to this, and remember, keep thinking on paper.